Hello everyone, this is Junzhuo. It's my great honor here to present our work, LVF Gene, Efficient Liberty Variation Format LVF Generation using Variational Analysis and Active Learning. To begin with, at a nanoscale, no circuit parameters are truly deterministic. They are usually in the form of probability distributions. Take the transistor as an instance. The effective length and width of the thickness of gate oxide or the dopant density, they all are various and will significantly impact the circuit performance. So it's very critical to use the statistical static timing analysis. It propagates the timing distribution rather than a timing value in analysis. However, the timing distribution requires the statistical characterization, which involves the multi-color simulation. It's too time-consuming and then limit the large-scale applications of SSTA. In common SSTA, people use the Liberty Variation Format (LVF). It used statistical model with three moments to describe one distribution. Same to Gaussian distribution, the first two moments are mean value mu and standard deviation value sigma. And it also used the third moment gamma so that it can describe the degree of skewness. And it used three n by n lookup table to record n by n timing distribution. Each of them correspond to three parameter moments. Here, the lookup tables are in the form of Liberty, the .lib file that we are very familiar to. In this work, we propose the LVF gene, which aims to speed up the total simulation time of LVF characterization. The motivation is we found that the process variation impacts the timing in a predictable way, so we can do spec simulation for one part of samples and use those data training a surrogate model to replace the spec simulation and then predict the rest samples and finally estimate the entire timing distribution with the surrogate model. It is an active learning algorithm, which means it will progressively selecting the most effective samples according to our proposed acquisition function. Here is the overview of the proposed LVF gene. It's an iteration framework. Basically, for each iteration, we train the surrogate model with current observed samples and timing, and then predict the timing for all candidate sample sets and estimate the distribution with the prediction. Then we evaluate the acquisition score for each candidate samples, and according the acquisition score, we select some sample to do the real spec simulation to obtain the timing. Then we can update our surrogate model and for next iteration. I will introduce each of part later. First part is surrogate model. It plays the same role as real spec simulator. We provide the process variation samples and it will predict the timing. That's the regression task. We use a deep GP as a surrogate model, where it consists of two parts, the multilayer perceptron and the Gaussian process. We use the MLP to perform the dimension pruning because we need GP to predict uncertainty, but GP perform bad in high dimensionality tasks. We found there are many inactive or useless process variation dimensions. For instance, in this 9-2 circuit, when the pin A1 is falling while pin A2 stay at high voltage level, the transistor MP2 is always turned off, and then the MP2's process variation dimension won't impact the timing. So we want to fit and prune those inactive dimensions by the MLP. Then it will pass the low dimension data to GP. Then for each iteration, we firstly training it with observed sample X and timing Y. Then we use surrogate model to predict all candidates' samples timing. We can get both Y's expectation and uncertainty, where we can use the expectation to estimate the timing distribution and use the uncertainty to evaluate the acquisition score. Then we want to propagate each sample's timing uncertainty into its influence contribution for final distribution, also as known as the acquisition score. There are many equations in our paper, but to summarize them, we firstly compute the contribution from the timing uncertainty into each moment uncertainty, and then we evaluate each moment uncertainty towards the entire timing distribution's uncertainty by the variational analysis. You can imagine we just apply some small perturbation on each moment and observe what's the influence from this small change uh, onto this timing distribution. And after that, we can also perform the multi-timing co-optimization. We just simply weighting each timings, for example, the delay, transition, and setup or hold timing acquisition score together. So we get overall acquisition score for co-optimization. When we get the acquisition score for each samples, we want to judge if one sample need or needn't the spec simulation by its acquisition. Uh, and the key point is we want to avoid all the selections that come from the same maxima area. We want to make them as separate and uniform as possible. So we use the local maximal in multi-dimension space, and then we do the bandit. It just the idea of it is the possibility to be select is come from its value. After that, we obtain the select sample batch, and we use these samples to do the spec simulation and to perform the next iteration. Now we have go through one iteration for LVF gene, and let's back to the overview and then go to the experiment part. In our experiment, our simulation used the TSMC22 library with TD corner, 0.8 watt and 25 degree. As the golden, the results come from the random Monte Carlo with 100,000 samples. And we use the Jensen-Shannon divergence to measure the distribution's distance. And for the measures to compare, we compare for the random Monte Carlo simulation and the Sobo's Cauchy Monte Carlo and our proposed LF gene. In first experiment, we validate our work with a 48 dimensionality null-2 circuit and use 32 samples for each iteration, which also is the batch size. And it is a delay transition timing co-optimization task. And you can see that the orange estimate distribution rapidly converge to the blue golden distribution. And you can also use the J divergence to confirm that observation. Still, in these experiments, we use J divergence to quantify occasionally compare the LF gene with random and Sobo's. We can find that in both the convergence and speed up rate, our LF gene is the red curve. It always performs better in the convergence and speed up rate. In the second experiment, we validate the speed up for the MVF on the entire circuit library. We do the validation on 26 different circuits with the same timing arc and 8x8 different slow load pairs. Then we evaluate the speed up rate on different accuracy level from 5,000 to 10,000 Monte Carlo random Monte Carlo, and we can find that the IVF gene achieves up to 4 times and 2.3 times speed up compared to the Sawball's algorithm in the delay and the transition. In the final experiments, we validate the application to real timing analysis. We perform the prime time SITA task on the ISCAS 89 circuits benchmark, and the libraries are generated from the 5K sawballs and 0.7K LF gene, where the runtime of the sawballs is 290 hours, while our LF gene only use the 80 hours, which is 3.5 times speed up. Well, in the table, you can find that there is almost no accuracy lost. So we can say our LF gene can perform the characterization very faster with almost no accuracy lost. Now, let me briefly go through the summary of this MF gene. It can generate high accurate LF library with much less simulations, and for the cells characterization, it can achieve 4 times overall speed up compared to the sawballs in delay timing, and 2.3 times in transition. And for the real path timing analysis, it can achieve 3.5 faster from 290 hour to our 80 hour, and it is almost no accuracy lost. And for the future work, we can improve the robustness, and we can improve the algorithm for the setup and hold timing characterization. Okay, thank you for your listening.